In today's video, we are going to practice applying the ideas that we explored in videos 9 and 10 to construct some sinusoidal functions which actually represent some real-world cyclical behavior or wave patterns. That's the only goal for today, to set up those functions. The first sort of quintessential situation that can be represented by a sinusoidal function is an object which is bouncing up and down on a spring. So we have an object which is hanging from a spring. When you attach an object to a spring and you just hang it there and don't mess with it at all, it naturally hangs at a certain position. The position of the object depends on the object's weight. The heavier the object is, the lower down it will hang. And it also depends on the spring's rigidity. If the spring is really stiff, then it won't stretch out as much when an object is attached to it. But if the spring is really stretchy, then it will stretch a lot when an object is attached to it.
You'll be surprised how many springs really behave very nicely, according to Hooke's law. I have one here. That's not a very expensive spring. You see it here. And there is here a holder onto it, so it's already a little bit under stress. That doesn't make any difference. These marks here are 13 centimeters apart, and every time that I put 1 kilogram on, you will see that it goes down by roughly 13 centimeters. It goes down to this mark. I put another kilogram on, it goes down to this mark. I put another kilogram on, and it goes back to this mark.
When you attach the object to a spring and just let it hang, we call that position 0. This is also called equilibrium position. Okay, so we have this object attached to the spring, hanging at equilibrium, and its equilibrium position is what we will represent by y equals 0. If this object ever ends up below its natural position, we're going to call this negative y. And if this object ever ends up above its natural equilibrium position, we will represent this with a positive y value. Okay, so we come in and we grab hold of the object on the spring, and we pull it down and then release it. Sam, play the clip. Once you do that, the object will begin to bounce up and down.
The period of the motion is the time required for one oscillation. Boom, boom, boom. So it's the time between booms.
So someone says, okay, this object is now bouncing up and down, so its position is going down and then up and then down and then up and then down and then up. So over time, we can see the position of the object follow this up-down sine wave pattern. So let's try and construct a sinusoidal function which matches this pattern. Now the first thing that we need to do whenever we're answering a question like this is we need to identify the amplitude, the period, and the midline for this cyclical behavior. So let's go back into the question and see if we can figure out what is the period, amplitude, and midline for this particular cyclical behavior. So they say, all right, the time between bounces is 1 second. So from one bounce to another, 1 second of time has elapsed. So from that, we get the period of the wave. It takes 1 second, 1 in the units of seconds, for the bouncing object to complete one full cycle of motion to go up and then back down again. The distance between the object's highest position and lowest position is 4 inches. So what are we being told? We're being told that if we look at the distance between the peak and the bottom, that distance is 4 inches in total. So if it's 4 inches in total, if I split the difference, it must be 2 units to the maximum and 2 units to the minimum. So from that, we can get the amplitude. The amplitude would be the distance between the middle of the bouncing motion to the highest point of the bouncing motion. The amplitude would be 2 units. Now, what would be the midline for this movement? Well, the object is bouncing down and up around its equilibrium position, which we were told is being represented by a height of 0. So the midline, based on that data, would be at the equilibrium position. The midline is y equals 0. Now, step number 2 is to use this period, amplitude, and midline to write down a formula for the sinusoidal function that also has these features. So I'm going to use that formula which says that the function that you can use is take the amplitude, in our case 2, take sine of 2 pi divided by the period, multiply that by the input t, and then add the y value of the midline. So cleaning this up just a little bit, we get that f of t is equal to 2 sine of 2 pi times t plus nothing. There's one last detail that is sometimes useful to consider, and that's to potentially include a phase shift, a horizontal shift, so make sure that the wave that you have created reaches the maximum, minimum, etc. at the right time. Scrolling back up to the problem, I was told that the object was pulled down and released at time t equals 0. The implication of this was that the object was at its lowest point when t was equal to 0. So the wave that I construct, ideally, should be reflective of this data. Now let's graph our current function f of t and see if that's true. So here I am on Desmos looking at the graph of the function f of t equals 2 sine of 2 pi t. This sinusoidal function is currently a match to our real-world cyclical behavior in its amplitude, in its period, and in its midline. But presently there is a small discrepancy between the cyclical behavior that we're trying to capture and the wave that we have constructed. And that's that the object is not currently at its lowest position at time t equals 0. Currently, based on what we have created so far, the object at time t equals 0 is at equilibrium position. The y-coordinate also is 0. So if I wanted to have the object be at the lowest position at time 0, I would have to put a horizontal shift into my function. And there are a couple of different shifts that are possible. One potential shift, for example, to move this minimum point 1/4 of a unit to the right. That way this minimum point will end up at time t equals 0. But there are lots of other different shifts that will also work. Another way to move one of the minimum points toward t equals 0 is to shift the graph by 0.75 units to the left. That will move this minimum point over to the y-axis. Because of the repetitive nature of sine, there are going to be a bunch of different shifts which all have basically the same effect on the graph. So you can choose whichever shift you prefer that for this particular problem will get the minimum point over here to time t equals 0. So currently, our function f of t equals 2 sine 2t reaches min point at t equals -1/4. We also saw that a min point was reached at +3/4, and there were several other times that the function achieved its lowest point as well. What we want is to have the min point at time t equals 0. So what I will do is I will take the function and horizontally shift it One horizontal shift that would work is by 0.25 units to the right. That'll move that minimum point from t equals -0.25 over to t equals 0, which is what we're looking for. But other shifts are possible. Another correct answer would be to shift it by -0.75 units to the left. Now to shift something c units to the right, let's recall from pre-calc 1 that if you take your t value and you subtract some number, let's call it c, this will shift c units to the right. And if you take your t value and add c to it, this will shift c units to the left. So if I wanted to shift my wave pattern so that it was reaching the minimum at the right time, one possible answer would be to take my sine function f of t, which is equal to 2 sine of 2 pi times, but not 2 pi times t. I'm going to take that 2 pi and multiply it by the quantity where t has been replaced by, for example, 0.25. This will shift the graph 0.25 units to the right. So this will be a wave pattern which not only has the correct amplitude, period, and midline, but also reaches the correct locations at the correct times. Another possible answer would be to use f of t equals 2 times sine of 2 pi, but this time I'll replace t with the quantity t plus 0.75. This equation would shift the graph 0.75 units to the left. Oops, I shouldn't have this minus sign here. This would shift the equation 0.75 units to the left. So this would be another way of changing the time so that the object was at its lowest point at time t equals 0. Let's go ahead and check on Desmos that both of these answers are correct. So here was our original guess at a wave pattern, which did match in terms of amplitude, period, and midline. If someone also requires that the wave matches in terms of when it reaches certain positions, then I could use, for example, parenthesis t minus 0.25. And we can confirm, okay, In this picture, now the object is pulled down to its lowest point at time t equals 0, and then it's released and bounces up and back down, up and back down, up and back down. Let's also check that the other possible answer of plus 0.75 will work, and sure enough it does. And as a matter of fact, you get exactly the same graph. Whether you put in plus 0.75 or negative 0.25, the exact same wave pattern is achieved. Because of this repetitive nature of sine, different horizontal shifts can have the same effect. Now, just as a comment, you really do need to make sure that your t plus 0.75 or t plus whatever horizontal shift is enclosed in its own set of parentheses. If you don't include the 0.75 in parentheses, the horizontal shift will be distorted. So to give you an example of what it looks like when you don't have the parentheses around the 0.75, you get this green graph, which certainly does not achieve its lowest point at time t equals 0. So this shift is all messed up. If you want to get the correct horizontal shift, the t and the shift have to be together in parentheses. So let's do one more exercise as a demonstration of the general technique. So in this exercise, we're having a look at the cyclical behavior, which involves number of daylight hours per day as it varies over the course of a year. Now in Washington State, it looks like we reach a minimum of 8.42 hours on December 21st, which occurs 354 days after the first day of the year, and a maximum value of 16 hours per day of daylight, which occurs on June 21st, which is 171 days after the first. So someone says, okay, I'm interested in a sinusoidal function which represents this situation. So I want to match the amplitude, and I want to match the period, and I want to match the midline of this cyclical behavior. But also I have a request. I want to make sure that time t equals 0 corresponds to the first day of the year, January 1st, the beginning of the year. So step number 1, let's identify the amplitude, period, and midline appropriate for this situation. So we have time passing in days along the horizontal axis, because we're dealing with t in days. And vertically, let's represent hours of daylight. The wave reaches its maximum 171 days later. So at t equals 171, the number of hours of daylight has reached its maximum around 16. And if I look 354 days after the start of the year, t equals 354, at this point the number of hours of daylight has reached its minimum down here at a minimum value of 8.42. So let's have a look at this wave pattern. In my opinion, the period is the easiest one to identify because that one is pretty intuitive. We can guess that this cycle will repeat every year. So I'm going to go ahead and say that a year is, for the most part, equivalent to 365 days. I'm going to just ignore leap years because they form unnecessary complications for this kind of problem. Now let's try to figure out, perhaps, what the midline would be. The midline occurs directly between maximum and minimum. And to find the number which is directly between y equals 16 and y equals 8.42, what we can do is take the average. The average of the maximum value and the minimum value is equal to 12.21 if I have that correct. So this would be the height of the line that cuts this wave pattern in half. Now what about the amplitude? The amplitude would be the difference between the midline and, for example, the maximum value. So let's go ahead and figure out the amplitude by looking at the difference between the maximum value of 16 and the midline value of 12.21 is 3.71 hours. So step number 2 is set up a sine function with these features. So I'm going to set up the function where we have the amplitude out in front, 3.79. I'm going to take sine and do 2 pi divided by the period, which was 365 days. And then I'm going to multiply it by t. And then I'm going to add the midline. Step number 3. If necessary, to get the wave to match the data in the problem, let's horizontally shift. So here I am on Desmos, looking at the current best guess that we have of a sinusoidal function which matches the real-world cyclical behavior. Now, currently what I can see, based on this picture, is that this object reaches its lowest point not at time t equals 354, but at this weird time 273.75. Likewise, the date at which the highest number of daylight hours is reached is incorrect. Currently, it's being reached at day 91, roughly speaking, 91.25 instead of day 171. So what I want to do is I want to move this 90.25 some number of units to the right so that it's over here at t equals 171 instead. So let's figure out how much I would need to increase 91.25 to move that maximum point over so that it occurs at time 171. The amount of shift that would be necessary to move that peak from 91.25 to 171 is equal to 79.75. We would have to move the graph this amount to the right so that the peak, the maximum number of daylight hours, occurs on the correct date. So, having established that, what I'm going to say for my final answer is this. The function, the mathematical wave, which captures the real-world cyclical behavior of daylight hours, the amplitude was 3.79. The period was 365 days. The midline was 12.21. And in order to get the exact dates to line up, I'm going to take my t and I'm going to subtract 79.75 in order to get the dates to align perfectly. So here is the graph of our wave, here with the correct amplitude, period, midline, and shift. And by shifting the function, we have gotten the maximum point to be achieved on the correct date. Now, as a heads up, because we did decide to ignore leap years, there is a little bit of a rounding error to do now with the winter solstice, which is being predicted to occur 353.5 days from the start of the year instead of exactly 354. That's because a year in reality is not exactly 365 days long. It's 365.25, etc., etc. So that's the general process. I have demonstrated the idea with 2 examples, but that general process can be used in quite a number of different examples. To summarize what we did, reading the question and maybe plotting a couple of points on a graph if you're visually inclined, determine the period, amplitude, and midline of whatever cyclical behavior you're examining. Once you've identified those features, sketch a basic sine function that has those same features using the formula that we gave in the previous video. Then check to see if your question is giving you any data about what the wave is doing at any particular time. You may need to horizontally shift your function in order to get the waves to completely line up. So I recommend to graph your original guess, check to see, how much do I need to shift this function to the left or right to get it to achieve the correct behavior at the correct time, and then incorporate that shift into your function by either adding or subtracting a number to your input. Now, to segue into what we're doing tomorrow, let me pose the following question. Suppose that we wanted to figure out the dates at which the number of hours of daylight was equal to 10. So we want the times, we want t, the days, when the number of hours of daylight, as predicted by our formula, produce the number 10. The question is, how do we actually solve an equation like this one? How do we take this equation and algebraically manipulate it to eventually get something that looks like t equals number? We can get rid of the 3.79 and the 12.21 easily enough just by subtracting that 12.21 and dividing out that 3.79. But the big issue is that currently the t is trapped inside the sine function. So how do we get t outside of the sine function? And that is what we will be studying tomorrow.